Welcome to the lecture on equal payment series and gradient series factors. So, yesterday in the last lecture we had an overview of the compounding factors, and in that we discussed about different type of factors like we have a compound amount factor, we discussed about the present worth factor. Then we also had the discussion about the equal payment series factors, but in that we discussed about the equal payment series compound amount factor and sinking fund factor. So, in the compound amount factor, as we know that you have to multiply this factor with the equal payment annual payment, and that will give you the future amount, and reverse of that factor is the equal payment series sinking fund factor, where the factor will be multiplied with f future amount, and that will be giving you the equal annual amount. So, that is what the two factors we discussed. Today we are going to discuss furthermore about the equal payment series factors. Among them there is a factor known as equal payment series capital recovery factor. Many a times when we talk about the financial transactions, we are concerned to know that whatever we have a capital, suppose somebody has a capital or the sum of money is there in the bank. Now, from that amount, since he has kept in the bank, if there is no interest earned, then you know that how long it will last if you are taking annually certain amount. Like if you have 1 lakh and every year you want to withdraw 10,000 rupees, then you know that it is going to last for 10 years, and in 10 years it will be vanished, provided there is no interest earned on the capital. However, when we talk about the finance related issues or economics related matters, in those cases we know that whenever we have any investment, we are going to earn on it, because that will earn certain interest. Now, this interest, because once the time will proceed, then there will be interest earned. So, we need to know that what should be the equal annual amount which can be taken out, so that as the time progresses in a certain amount of time, the capital plus the interest earned on it, all together you can utilize it fully. So, that is how this factor is defined, that you are recovering the whole capital, and since the capital is also earning interest. So, the cash flow diagram will go like this. You have one P at present, and then you are going to have an equal amount every year. So that it will, after n years, it will be completely over. So, basically this is this is the factor which is multiplied. So, this amount is A. So, this factor, when multiplied, so multiplied with P will give equal annual amount. So, you know the capital amount, that is P, and this capital is to be recovered, and that is how you need to know the value of this factor, which will be multiplied with p, and that will be giving you this the value of a. So, how much you will be getting every time. So, basically what you do is that here you have the factor that will be defined as a by p and I and n. So, this is the factor which is known as the equal payment series capital recovery factor, and this factor, when it is multiplied with p, then it will be giving you the a. So, this factor is known as equal payment series capital recovery factor. So, how to get the expression for this? So, we know that earlier we discussed that a will be f into I upon 1 plus I raised to the power n minus 1. So, we have discussed about the equal payment series compound amount factor and equal payment series this present worth factor, that was sinking fund factor was there. So, we are going to have, so we are going to use that expression only. So, this from this now we further know that f is equal to p into 1 plus I n. So, this is equal payments. So, this is basically the compound amount factor 1 plus I raised to the power n. So, if this f is replaced with this expression, then it will be equal to a equal to f into I into 1 plus I raised to the power n and divided by 1 plus I raised to the power n minus 1. So, basically what we see is that this is not f now, because this will be p. So, what we see that when p, your capital, basically this is multiplied with this factor basically is that gives you a. So, this factor is known as equal payment series capital recovery factor, and that is why this factor will be equal payment series capital recovery factor, that is a by p I n. So, this is something about you must know, and there are many examples of such factors used, like there are many cases when somebody will put some amount in the bank. So, for the maintenance of, suppose some garden or maybe certain colonies for a certain period. So, the amount, suppose somebody has put in 5 crores of rupees for getting the monthly amount as well as and so somebody wants to have annual amount. So, from 5 crore he will be getting the interest, and what should be that amount every year for 20 years. So, that the society may require it for many purposes, like for giving the salaries, for for making other infrastructures or so. So, that way in those cases you need to have the use of such factors, like you have 5 crore here, and then suppose rate of interest is defined. So, it will be 0.1, 10% interest is there, and then NE will be 20. So, you can use these formulas to get equal amount which you will be able to withdraw it every year, and at the end of 20 year this whole amount will be nil. So, that is how the use of capital recovery factor can be justified. The next factor will be the equal payment series present worth factor, and for that again we will see that it will be the reciprocal of this factor. So, it will be equal payment series present worth factor. So, in this case what we try to get is in this case you know the equal payment amount and you have to find the present worth. So, it will be basically P by A I n. So, this is the factor which is known as equal payment series present worth factor, and this is reciprocal of A by P I n. So, A by P I n we have seen that it was I into 1 plus I raised to the power n by 1 plus I raised to the power n minus 1. So, it will be reverse of that and it will be 1 plus I raised to the power n minus 1 divided by I into 1 plus I raised to the power n. So, this factor when multiplied with A, it will be giving you the basically the present worth. So, how much should be basically when you require to know that how much should be invested now, what should be the capital now, so that you are going to get a certain amount of A equal year end payment for certain period. Suppose for the maintenance of the society and for the staff and all other things you require 10 lakh rupees every year end. So, and that too for the 20 years. So, for that if you how much you should have the capital now, so that from that interest will also come, and as the time because as the time progresses the amount will be withdrawn. So, the interest earned will be slowly less, but then the thing is that at the end of 20 years this whole amount is exhausted. So, in those cases when you have to find the present worth, then you are going to use such factors. So, that we will talk about finding the P when A is given, and this series for the factor which is used for such calculations. So, these factors are known as the equal payment series present worth factor. Now, as we discussed that these payments normally by convention they start from the first year. So, you will be starting, so any amount suppose you have invested and you will be getting return from the first year onwards. So, that is what the convention is, and they are known as annuities, and that is what the amount is A. So, you may have P and then it will go for n years. Now, the thing is that many a times what happens that your amount which is started, the equal year end amount which has to be started, that is little bit delayed. So, this delay is basically known as the deferred time, and in those cases they are known as the deferred annuities. So, the thing is that the cash flow diagram will look like, not here 1, 2, 3, 4 is nothing, but it will start from the fifth one. So, it will be again A, and it will be 1, 2, 3, 4 is there. So, 5, 6, 7 and then it will be n. So, these are the typical examples are in the case of loans which the students take. So, they tell that till they get the job they should be they should not be told to pay. So, maybe for 4 years they are not paying, and then they are starting paying from the 5th year. So, such are the cases of the deferred annuities, and there are ways to find, because now in these cases what you will do that for this series you may have either P here or F here, equivalent value calculation, and then you can have the amount of P to be calculated. So, such cases are the examples of deferred annuities, and we will have more such problems we will encounter when we talk about the economic equivalence, how to calculate in those cases the cash flow diagrams, equivalent values, how they are calculated, that we will discuss. Now, we will discuss about the uniform gradient series factor. So, we are the title shows that we are going to discuss about equal payment series as well as the gradient series factor. Now, the gradient series factors, as we discussed in our previous classes, they are of two types. One is uniform gradient series factor and another is the geometric gradient series factor. So, uniform gradient series factor we will derive in this lecture. Now, what this uniform gradient series factor talks about is that when we are paying the amount by a gradient uniformly. So, suppose we are taking the example of a loan which is taken by the student to study. Now, this person is going to pay the loan, and in the first year he is going to pay maybe 1,000 rupees or maybe 10,000 rupees in a year, and from the second year onwards he wishes to pay every year 1,000 more, because he is expecting that there will be salary hike. So, on that basis he can expect that he will be able to pay more. So, in such cases how you should be able to find the factors, you should be able to find basically what will be the present worth or what should be the future worth of such factors, or what is basically the equivalent annual amount for any such type of series. So, basically we are going to discuss about it. So, in fact what we do is for such cases we find the equal annual equivalent amount for any such series. So, now what we see is normally such series means so you start from 0 time. In the first year it will be paid, you will be paying A, and in the second year you will be paying A plus G. So, in the third year you are going to pay A plus 2G, and in the fourth year you are going to pay A plus 3G, and fifth year you have to pay A plus 4G. Like that it will be moving, and in the n minus first year you are going to pay A plus n minus 2G, and in the nth year you are going to pay A plus n minus 1G. So, these are basically, so this will be further larger. So, this is the example of, so what you see is that there is a gradient, this is maintained, this is a straight line basically, and every time as compared to the previous payment, it is always larger than by a fixed quantity. So, it may be either larger or it may be smaller. So, it may be so that it is large here A, and it may be A minus G, A minus 2G, A minus 3G, like that. So, that also may happen. So, that will be a decreasing series, and this is an increasing series, uniformly increasing series, and this is, and that may be a uniformly decreasing series. Now, the purpose is that how to represent such series, and our job will be to find basically equivalent values. So, what should be basically the equal annual amount for such series. So, what amount will be basically equal for such gradients. So, basically what we see is that if you look at this series, you see that A is fixed here, A is always fixed, but the gradient is changing. Now, at this point this is 0, at this point basically there is the gradient amount is 0. So, it is only A. So, if you take A out of it, so it will be, so the gradient value, if you look at, gradient value will be 0 here, and then at 2 at this place it is, so you are going to subtract A from every receipts or disbursements, and this point you will have G. So, then at 3 you will have so that way your things will be moving. So, this way your gradient will move. So, you are going to have to come to this n, and your grade, these are, so G, so G, 2G and then 3G and all, it will be moving, and this will be n minus 1 into G. So, what we see is our job will be to have the cash flow diagram, which will be talking about the equivalent value, equal annual amount which should be same as the amount which is calculated from this place. So, here it will be A and A and A. So, basically what we do is we know that this is A is anyway fixed, but for this gradient amount which is being paid onwards, what should be the equal annual series for that gradient amount, and that is why this is known as a uniform gradient series factor. And once we get that A, then the small capital A plus small a basically will be talking about the whole equal annual series for the whole transactions. So, that is what we are going to talk about. And so, what we can see by in the tabular form, if you talk about the end of year, and then if you go the gradient amount, then if you take set of series equivalent to gradient series, and then you have annual series. Now, what we see is that your end of year is here we have defined. So, it will be 0, 1, 2, 3, 4, and then it will come as n. So, before that there may be n minus 1. Now, what we see is we know that anyway in the first year also gradient amount is 0. So, anyway it is 0 here, and the second year we start with gradient amount g, then third year we get 2g, then fourth year we get 3g. So, it will be in the nth year it will be n minus 1 into g. Now, if you take up the set of series, so it will be 0, 0, and then you have g here, and you can see it will be written g plus g. So, it will be further written g plus g. So, if you take n minus 2g, so it will be g plus g plus g plus g, and in the last you will have all that extra g. So, these are basically the equivalent to gradient series the g values, and anyway we are going to have this particular A. So, we want the A to start maybe, because in the 0 year we are not getting, we are getting from first year end. So, we will have A. So, what is there that we want to have this A, we want to find this A. So, basically what we mean to say that we wish to have this as equivalent to the capital A, and that will be calculated by using the expression. So, if you look at this as you know, you have the payment of A first year end to the nth year, and if you take its if you want to have the F, so what is a final future amount. So, this A must be multiplied with the factor F by AIN. So, basically the A will be multiplied with F by AIN. This will give you the future amount, that is the accumulated amount at the year end. Now, how much it should be equated, how this should be equated? What we see that now this is the value at this time. So, at this time if you look at this g, basically 1 g is this g has is not adding any value. So, you have to simply add g. Now, if you come to these 2 g's, so here the amount will be g into F by AI2, because these are the two values, and you are getting these two year end values. So, it will be g into F by AI2. So, this way it will go up to F by AI n minus 1. So, you can have this as g, that is the last one, then another g, there are 2 g's. So, it will be g into F by AI2. Similarly, g will be F by AI3. So, this will go up to g F by AI n minus 1. Now, we know that F by A, this is I1, this is I2. Okay. Now, so what we do is we will go further, and what we see is that we can have G. Now, this one we can write 1 plus I raised to the power 1 minus 1 by I. So, it is G. Then as we know that for this factor it becomes 1 plus I 2 minus 1 by I plus G 1 plus I 3 minus 1 by I. So, like that it will go, and it will in the end it will go 1 plus I raised to the power n minus 1 minus 1 by I, because we know that f by a I n will be 1 plus I raised to the power n minus 1 upon I. So, that is how it goes, and this is 1. So, this is similar as 1, because f by a I 1 will be 1 itself. So, we can further write, we can take G by I out. So, what we see is that it will be 1 plus I n minus 1 plus 1 plus I n minus 2, and all that it will be moving. So, you are coming up to 1 plus I raised to the power 1. Up to this we are coming, and then ultimately we have this one term coming, you know it is coming for n minus 1 times. So, it will be n minus 1. So, further we are getting G by I, and then you have you will be coming to 1 plus 1 plus I think it will be there are this 1 is coming as n terms. So, I think this will be n. So, you will have n here, and then that is why your 1 will be coming like this. So, 1 plus I, and then so it will be similar. There are n minus 1 terms basically. So, we have n minus 1 here, and this 1 will be added. So, 1 plus I plus 1 plus I 2. So, it will go up to 1 plus I raised to the power n minus 1. Then you will have minus n g b I. So, this n will be taking out, and it will be n g upon I. So, this is basically a geometric series, and we can write it as G by I, and as we know that A is the first term and this is your common difference. So, it will be, and if you look at, you have n terms now. So, 1 plus I raised to the power n minus 1 and divided by r minus 1. So, it will be I. So, this is the term you are getting here, minus n g by I. This is what you are getting. Now, if you look at this A, so this f by a I n we know that it is 1 plus I raised to the power n minus 1 by I. So, it will be divided. So, A will be equal to, now we have this G by I, and you have 1 plus I raised to the power n minus 1 divided by I minus n g by I, and this all is to be divided with f by a I n. So, f by a I n is 1 plus I raised to the power n minus 1 divided by I. So, as you know that this factor will be, when it is separately multiplied. So, this will go and it will be g by I. So, what you see is that you can write, it will be basically g by I will be the first term, and then you will have this one n g by I and into. So, this will be n g by I, and then it will be I upon 1 plus I raised to the power n minus 1. So, if you look at it will be minus n g upon I, and this I will be vanishing. So, n into g divided by 1 plus I raised to the power n minus 1. So, what you see is you can have g as common, and it will be 1 by I minus n upon 1 plus I raised to the power n minus 1. So, basically this gives you that A, and this A we will be talking about the equivalent amount for the gradient amount. Suppose you are increasing, you are giving, you are depositing or you are getting 700 in the first year, and from the second year onwards 100 each increasing. So this is for the 100 increase, that value will be given by A. And if you talk about the total equivalent annual amount, it will be 700 100 plus that calculated amount for that extra 100 every year. So that way you can calculate these values using this factor, and this factor basically is known as the uniform gradient series factor. So you can have the name like uniform gradient series factor. So this will be basically multiplied with G, that will be giving you A. So it will be A by G I n. So if you this factor is multiplied with G, it will give you A. So this factor becomes 1 by I minus n upon 1 plus I n minus 1. So this is the uniform gradient series factor. So that's how we calculate it, and we can discuss some questions based on that when we discuss in the tutorial classes or the assignment classes in the end. Thank you very much.